Hello, Physics 1. I think I might have been doing this for a bit too long. I'm starting to get confused. All right, so welcome to part 1 of Monday's lecture, week 16. We have one more week after this. We're going to make it through the most challenging and interesting semester, I hope, of your lifetimes. I really hope all of your academic experiences after this are dull and boring, predictable, and uninteresting with no adventures. Like this. I hope you learn interesting and adventurous things from, classrooms with people in them. All right, so we have been in chapter 5, which is all about collisions. And that's really where we bring together the energy principle and the momentum principle. So 2 of the most important principles we cover all semester. So the other one is the angular momentum principle, which is what chapter 11 is all about. And if we get to chapter 12, we're going to see some really fun things with internal energy, but, we're going to play that one by ear. So one of the things that we have introduced is that the perspective of the observer matters when we are making measurements in physics. And this is really a profound idea. It was developed with Einstein's theories of special relativity, and it had implications for things like quantum mechanics, and it really made that transition into modern physics as we know it today. And one of the reasons I like this particular textbook is it really starts to bring that in now, so that you're not, even though we are studying classical versions of physics, meaning Newtonian physics, we are already beginning to introduce this idea that reference frame is important to how we study this particular field. And so should any of you choose or find yourself later in a position in life where you're doing more physics, you already have some instruction on how to really think about these things, what types of questions to ask, that can really just lay a really nice foundation for you. Okay, so long introduction over. A frame of reference is the point of observation. So in this class, now this will get more complex if you take advanced physics beyond 1 and 2. For this class, there's really only 2 options. So it is either at rest or moving at constant velocity. So we have no accelerating reference frames. That gets a bit trickier to analyze. So if it's not constant, we need different physics. And I believe we'll do a couple accelerating reference frames in Physics 3, which is an option that I will make available to anybody who has taken the introductory Physics 1 and 2 sequence and Calculus through Calculus 2. So if you're curious in sort of some of the cool and sexy aspects of the field, you'll start to get to see that in modern physics. I highly encourage it. That was the class that really opened up my mind to why I was in such an amazing field. I liked physics in the introductory sequence, but I really felt so fortunate to get to study it when I started to get into physics like that. So, okay, so as we've already seen, the frame of reference affects energy. Energy accounting, the energy is what it is, but where you attribute it to depends on the frame of reference, and velocity observations. So we know this. And so velocity in a moving reference frame velocity is going to be equal to v prime plus v frame where v is the velocity in a stationary frame v frame is the velocity of the moving reference frame and v prime is the velocity observed in a moving frame. By the way, you never need to write down every sentence that I write down. I'm writing down more with these video notes than I would for an in-class lecture where I would just simply say more. The reason I'm doing that is just for clarity. So you can decide about how many notes you need, and your style doesn't need to match mine. You are in control. Okay, so using this, we're going to reanalyze the collision of the bowling ball and the marble in space with a couple modifications. So we did that. That was the last thing we did in class last time. So let's go ahead and look at that particular scenario again. So bowling ball, marble, collision in space from different points of view. It'll be like one of those sitcom episodes where you hear the story from different perspectives and it changes a little bit each time, only this is going to be scientifically accurate. All right, so just note names and spellings are previous students who have graduated and have no problem with me doing this. All right, so we have a student. She is sitting on an asteroid. There she is. So at rest on an asteroid. Yes, there are asteroids in the Kuiper Belt. So Kessa sits on an asteroid at rest, watching everything. So she's got a rest reference frame. Now we've got another student. So her name is Kaylee. There's Kaylee. Here she is. Okay. So she decides what she's going to do. So what we're going to have is we've got a bowling ball, and we're going to send it towards a marble. And there's going to be a collision. So instead of shooting the marble at the bowling ball, now we're shooting the bowling ball at the marble. So what Kaylee decides to do, so she's here. Put her right there. So that way I don't need to redraw. She launches herself so that she's going the same speed as the bowling ball, and she's just traveling alongside of it. So she's like, I see you, to the bowling ball. All right, so I'll write this out. Kaylee launches herself next to the bowling ball. at speed v. So bowling ball has speed v. Put some colors on here. And Kaylee has speed v. And Kessa is at rest, just eating popcorn and watching the whole thing happen. All right, so this is what we have going on. Now, remember, physics works in every reference frame. It's a very precise science, for the most part. In terms of modeling, like it's, you know, there's some rules we got to play by. Okay, so what's going to happen is the bowling ball, there it is, with speed v, mass capital M. It's going to hit our little marble, mass little m, presently at rest, and we're going to assume fairly elastic, or elastic enough for measurement purposes. All right, so what does Kaylee observe? In the world's most interesting and well-drawn comic. I mean, Frank Miller has nothing on these drawings. I'm kidding. My husband is the art major, not me. All right, so. So Kaylee will see bowling ball at rest. You say, what? They're both moving. Well, remember, from her perspective, essentially the idea is that you are always at rest and everything moves around you. So if the two of these are both moving with speed v, then it's like it's the same observation that as being at rest. And then essentially the marble, which is out here, will be observed coming towards her at speed capital V. Okay, so then there's a collision. Let's do this in orange, make it look like a comic book. They collide. Pow. Oh, and the reason we didn't do Kessa is we kind of, we're used to watching things from at rest. So what do Kessa and Kaylee see after collision? So let's do Kaylee first. Kaylee, with just two E's, sees the marble bounce off the stationary bowling ball with speed approximately V. So this looks the same. Actually, no, I have misread my notes. Red. This this looks the same as the previous example, where we had a marble bouncing off a stationary bowling ball. Okay. Kessa is going to see something a little bit different. It's going to be different from her perspective. So Kessa's going to see the bowling ball strike the marble and keep moving. With speed v. And now the marble has speed 2v. So there you go. Okay, so let's look at this equationally. So we want the velocities of both balls after collision. So V bowling ball is equal to V bowling ball prime plus V frame. So this is equal to 0, 0, 0 plus V 0, 0 is equal to V 0, 0. So this is the red V that we've seen before. And the velocity of the marble is equal to V marble plus V frame is equal to V 0, 0 plus V 0, 0. So remember, we're looking at this from moving reference frames is equal to 2V 0, 0. Okay, so, and we made the assumption, which was quite reasonable. And last year when I taught this, they did not believe me, so I pulled out a bowling ball and a marble and basically showed that there is no noticeable difference in speed when you have a bowling ball do this. Not in space, on a frictiony, dirty physics lab floor. It's pretty reasonable. That the change in speed in the bowling ball is negligible. All right. So that wraps up our reference frame discussion. You can expect that reference frame discussions are going to be a recurring theme all throughout the physics series. So 10.6, scattering, collisions in 2D and 3D. So scattering is how we do particle physics. We're all about crashing stuff into other things and seeing what happens. So typically what we're measuring and this could be in a particle accelerator, this could be in a neutrino detector, this could be in a dark matter detector, this could be in a laser Wakefield particle accelerator. So typically what is measured are the particle tracks, before and after collision. Our primary example for analysis will be the famous Rutherford experiment. So this is how we discovered the nucleus of an atom. Basically, atoms are mostly empty space. You've got a bunch of electrons around them, and then you've got a very tiny, very small, dense nucleus in the middle. So we were able to basically get rid of the Dalton model and get rid of the plum pudding model because of this experiment. So, okay, and the way this experiment worked is you had a bunch of gold sheets, were bombarded with alphas. So this was a particle collision experiment. So you have a gold sheet made of atoms, and you got a little alpha. I should have chosen a different color. Comes in, and you see what happens. So, for particle analysis, the before time is early enough. They are far apart. And the time after is also when they're far apart. And this is important because it means that you can analyze the energy of this collision without taking into account potential energy. So we know that we're dealing with a charged particle that's coming in, and it's going to interact with other charged particles, and so the alpha is positively charged, the nuclei is positively charged, and so in this case you're basically setting up a clever arrangement so that you have less to calculate. And you know what? Setting it up in a different way with more to calculate is still going to give you the same result. There's no cookies for doing things the hard way. You'll only get... Well, if you show me that, I'll be like, oh, I really appreciate all your work. You didn't need to do that. And if you had some of the professors I had who were German, I won't imitate their accents, but they would just look at you and be like, why would you do that? That's not a reasonable way to do this. And you just kind of want to melt into the floor while you're talking to them. All right, so here is the setup. And some of the German professors I had were incredible and amazing, would never talk to you that way. Actually, all of them were incredible and amazing. Just some of them had a way, really acerbic wit. Some of my Russian professors in grad school, same way, just really acerbic wit. And it's an experience. It's an experience that makes you better in life. All right, so set up. We have our alpha. I'm going to change colors just to make it more different. It's got mass. This is an alpha. It's got some momentum, 1. And it's heading towards gold. Mass M. This is gold. P2 equals 0 because it's at rest. And then, so this is before collision. Now let's look at after collision. So, you're going to have your alpha strike your gold. Oh, this is more during. Now we can do after. Oh, those of you that are education majors probably scoffing my inabilities to do multi-colored pens at the same time. Yeah, there's a reason I did not go into kindergarten teaching. Okay, so after the collision, your alpha is going to have some new momentum at a different angle theta because, you know, when we run two things into each other, let's see if I can get this here, you can get different angles. I would collide 2 marbles, but then I'd have to chase them all over the lab. And me bending down to pick stuff up these days is pretty hilarious and really uncomfortable for me, so I'm not going to do that. Okay, so, and this is a positive angle for the gold. All right, so this is basically what happens. They come in, they hit, and then after collision, they've got new momenta, and they've got what's known as scattering angles, which is all part of how momenta is conserved. Because remember, momenta is vector. It contains the angle within it. Okay, so now let's analyze using momentum and energy. We will start the alpha in x, and the scattering is going to occur in x and y. Okay, I'm going to start the equations on a fresh sheet of paper. And basically, this is a choice to make this easier. You can have scattering that occurs in x, y, and z. So with an LHC collider, and also the dark matter detectors that I worked on, you were looking at 3-dimensional scattering. But for really simple scattering experiments, and this one would have been pretty realistic to just be an x and y. Okay. We know that px initial must equal px final. Momentum is still conserved. So we have p1 is equal to p3 cosine theta plus p4 cosine phi, where this is for the alpha and this is for the gold. Okay. And py initial is equal to py final. Therefore, 0, because it's only in x at the beginning, is equal to p3 cosine 90 minus theta plus p4 cosine 90 minus phi. You want to look at those scattering angles again, just to verify this for yourself. Here they are. So you can see we've done the angles with respect to the x-axis, so you'd need to subtract the angle from 90 to get it into y. Okay, so Moving on, we also know this is going to be an elastic collision, or fairly elastic. K initial must be equal to K final. And we'll see actually why this was a really, really good assumption for Rutherford. So the explanation is coming. Okay, so therefore P1 squared over 2m is equal to P3 squared over 2m plus P4 squared over 2m. So one other thought on this. Remember, with particles, you can get true elastic collisions as long as you don't excite them into a different energy level. You have a 100% elastic collision for reals. Okay, so the final momentum, P4, so again, I'm just going to remind you which one is alpha and which one is gold. Of the gold nucleus, can be expressed as a vector. P4 is equal to P4 cosine phi cosine 90 degrees plus phi 0, nothing in Z. And then just something to note, we have known the masses of both the gold nucleus and the alpha for a while. So AU is, of course, the chemical symbol for gold. I'll give you the hint my 5th grade teacher taught me. AU, you stole my gold. You'll never forget it after that. At least I have never forgotten it. And I'm not a chemist, so I don't remember as many of these as other people do who are chemists. All right, and we have 3 equations. Oops, I'm ahead of myself. So one thing to know, so you notice I let you bring in formula sheets for your exams, and I just remember in my physics classes, there would always be some, do we need to memorize that? And some of my professors would just say, why would you waste your brain space on that? So there's a long tradition of just not emphasizing memorization. Of course, if you study for a standardized exam, you will need to emphasize memorization. But memorization is an easy skill to pick up. Invest in some note cards, practice it, and you can memorize. The harder skill is the understanding. So typically in a physics class, understanding is emphasized over memorization. Okay, so at present, we have, with this setup, 4 unknowns. P3, P4, theta, and phi. So this is assuming, of course, that we knew the momentum at which we sent in the alpha, which is a pretty reasonable assumption. You built the alpha gun, so you probably know the momentum that they're leaving. But we don't know either of these, and we only have 3 equations. So we're actually not going to solve the equations. What I'm going to say instead is this is the setup for doing particle physics. You will have your knowns at the beginning, which is going to be often initial momentum and energy. And then you'll have a series of unknowns. And then you'll need to make some decisions about what you want to measure to solve for what you don't know. So you don't measure all 4 of these in a particle physics experiment. So I'm gonna write a couple notes and then I'll tell you what they do. And I worked, Royal Holloway, where I went to grad school, has a very prestigious ATLAS research group. ATLAS is, of course, a research group associated with the LHC. And so I learned a lot about how they make their measurements from people that were actually doing it, which I consider to be just a real privilege to get to be around people like that. So insufficient to solve. And what they do is typically, in particle physics, we are measuring at least one other value. And using equations to solve for the rest. Every measurement device you put in there costs money, and also when you measure, you start to introduce elements into it. So there's a joke in an episode of Futurama, it's a quantum joke. They changed the outcome of the race by measuring it, which is a product of quantum mechanics. You do want to be careful about thinking about how to measure, so they use equations to solve the rest. So you'll have different segments of particle detectors. You'll have one that's measuring maybe angle, another section where they're measuring perhaps the momentum, and so on and so forth, so that they can put this all together and verify the result. But it's very unlikely you're measuring everything. You're measuring enough that you can then do very complex analysis to solve for the rest. So even in my experiment, so I did a scattering experiment looking at Rayleigh scattering in liquid argon. I measured some things and then calculated the rest. So I measured the number of particles that I was observing, and then based on models that I had made in computer simulations and the equations of attenuation of scattering, I was able to calculate what I couldn't measure. So I guess the point I'm trying to make is there's some very real-world examples for this type of physics, and this is something that we are using today to make cutting-edge discoveries. This is not just something that we used to do and now we've moved on. This is vitally important to how we understand the cutting edge of our own knowledge bases. And even on a practical level, this is what we do when we analyze things like traffic collisions, when we analyze roller coasters, when we look at things like bumper cars, when we do all of these engineering applications. The scattering equations are important. They're practical. They have real world implications. For those of you going into medical fields, this is important when you're looking at things like concussion, and you need to figure out how hard somebody's head was hit. You can use their momentum to go after this. So anyways, I will wrap up part 1 of this lecture here, and we'll pick up next time with an example.